Hello, North Tahoe High students. Welcome to one of our first class videos. This video is going to work for both the chemistry and the physics classes because it's fundamental to really all sciences. And what we're studying today essentially is measurement. So often people come into class thinking that chemistry and physics in particular are just math classes. And what that means is they don't really understand necessarily the role of math in a science course. We're going to find out that math always comes last in a science course, and the numbers always have meaning, so they're not just abstract numbers. Almost always in beginning science classes, the numbers are measurements. So that's what we're going to start with today, measuring. What can we measure, and how do we measure it? So as complex as some things get in math or in physics and chemistry, really it comes down to being able to measure essentially three main quantities that can be measured. We can measure mass, and the tool that we measure mass with typically in school is a balance, as a triple beam balance. I know you're familiar with those. We also have quad beams and some electric or electronic balances. We can measure distance or length, and the tool, real simple tool, we almost don't even think of it as a tool, would be a meter stick in that case, and we can measure time. A couple other things you might think about. We can measure temperature. We'll talk a little bit about what temperature is later in the course. And there's also something in electricity. We can measure charge when we study electricity and magnetism in physics, and bonding in chemistry, but we're going to leave those out for right now. We'll also talk in more detail later about the units. What are the ways that we can measure these things? But for right now, we can remember we're going to use the metric system. So the base unit for mass in the metric system is a kilogram. Base unit for length in the metric system we usually use is mass, or as meter rather, m for meter, and then time is almost always a second. And I said base unit in chemistry, in physics for mass is kilogram. The base unit itself is gram, but the most often one we use in physics is kilogram. So just a little bit of a heads up, we can do a lot with those units. There's a lot of other things that we can put numbers with in science. One of them that was commonly used, and most of us have some familiarity with, is the idea of density. Density sometimes is given by the Greek letter rho, and it's defined as mass over volume. Well, mass is no problem. We can take something, put it on a balance, and find it. But what about this volume thing? Well, if we think about volume as something maybe we learned in math class, a cube, then we find out really what is volume. It's a length and a distance times another distance. I used L's there. But those are all distances. So even though we have this thing mass over volume, it really breaks down to one of those three fundamental measurable quantities, mass and volume, which is essentially the same as this one. Likewise, there's velocity, which we'll study in physics a lot. That's distance divided by time, and distance would be a measure of length, and time would be a measure of seconds. So meters per second would be a unit for that. Again, we can measure distance and time. We can calculate lots of things with distance, time, and mass. So if we're going to use measurements as our numbers in a science class, we do have to talk a little bit about how well we make the measurements and what the measurements actually mean. So there's two terms that are important to scientists, and that's accuracy and precision. A lot of times these are thought to mean the same thing or being synonymous, but they're related, but they're not the same thing. Accuracy we usually define as how close to the truth a measurement is. The truth is in quotes in there because what we're really talking about is how close is it to what other experts have measured something to be. So there's measurement in there as well. Precision is how close a series of measurements are to one another, and are they repeatable. So a lot of times in beginning science classes you'll see this bullseye analogy where the truth is the target. So if we're close to the target, we're close to being accurate, we're close to being true. The precision would be the scatter of the bullets or the arrows in this case. So if we look at this one, here's the truth right there. We're kind of off of the mark, so we're not accurate, and there's a pretty big scatter, so it's not very precise. Look at this one though. This is kind of strange. It's accurate because the shots are kind of scattered around the truth, but it's not precise. They're not. You can't repeatedly hit that target or come close to that target. This one would be, if the truth is here, these are precise, we're hitting around the same spot each time, but not accurate. And then, of course, here's the best of both worlds. This is what we strive for, to be accurate and precise. But what does this have to do with measurements? Let's talk a little bit about that. All right, so we're going to use our accuracy and precision, our demonstration. We're going to use the idea of measuring the length of a pencil, mostly because we may have limited experience with a balance or using a stopwatch to 2 decimal places, but length is something most of us can grasp pretty quickly right off the bat. So let's take a look at this pencil, and let's put it up here on this first ruler here, which is measuring, this distance is 100 each time, right? 100 what? It doesn't really matter. It could be 100 meters. It would be a very, very long pencil. It could be 100 millimeters. That's probably close. That's more like 10 centimeters. But we don't really worry about the unit at this point. Let's just take a look at the different measurements that we can make. When we use this first ruler, the one up top, we only know for certain that we're between 0 and 100. So someone might come in and see this pen and they'd say, oh, that looks to me like it's at about 70. Someone else goes, no, I think that's 60. And then yet someone else could come in and say, no, that's 80. I think that's close to 80. So when we look at those numbers, same tool, same pencil, we could get a spread in here using this, and we'd have a spread in this case of about 20, between 60 and 80. However, if I move it down to the second one, we get to know something a little bit more certain. We know that we're now between, we are now between 70 and 80. And we're allowed to guess about how far between. I'm not quite halfway there yet, so I'm going to guess maybe it's about, I don't know, 72. Someone might say 73. And yet someone else might come and say, no, you're pretty close to halfway, 74. So just by having more lines on the ruler, we've been able to get our spread down from 20 to about 2. So, right, maybe we can look back, think about the last slide. This would be a lot of bullets sort of spread out around a target. Now we're starting to sort of hone in on a nice tight cluster of bullets on the target. Finally, we'll use the last one. Move it down here. And in this case, we know for certain that we are between, let me scrutinize this one right here, we're between 73 and 74. How far between that is up to a little bit of interpretation. Someone might say, I think we're at about 73.8. Someone might say 73.6, 73.7. But again, look at that cluster here. Now we're again have a difference in readings of 0.2. So we've gotten even closer, our clusters. So in this case, this is going to be the most precise ruler, and this would be the least precise ruler. But we do see, though, that if we can use a ruler properly, precision does lead to more accuracy. So they are related in that case. One thing that we set up here, what determines the accuracy? Precision is the lines on the ruler, how increment it is. Accuracy is always kind of a user error issue, whether you use the tool correctly or not, whether it's been calibrated correctly or not. For instance, if I put that pencil up there and I say, that's like 200 long, I'm just not reading it right. Or imagine this, I just put it over here and I say, that pencil's over 100. I'm not using that simple tool right. So accuracy almost always comes from someone using the tool incorrectly, or maybe the tool itself is broken. Precision is determined by the tool itself. So in this case, it's the graduated marks. So when we are using a tool properly, we want to be as accurate as possible. We also want to be as precise as possible. So this leads scientists to develop something that's referred to as significant figures. What is known reliably and what is estimated. We have rules for that, and that's what we're going to take a look at here next. So significant figures are figures that are reliably known. And when we're measuring, it's kind of simple. You must make one estimate and you must stop recording after you've made that. So let me give you an idea of what we're talking about. We have 3 rulers and I've adjusted them a little bit. This has just 1. This is the same length, but it's been broken into 10, so we have a 0.9 right here, then 1, and then 1.1. So it's the same ruler, right? And then this one has been subdivided by 10 yet again. So let's take a look at this and figure out what we can say for certain and what's an estimation for each one. So let's take a look at the first one. Here's a 1 right there. We know for certain then that our ruler or our pencil is between 0 and 1. It would be wrong of us just to say, oh, it's 1. Because we know for certain it's not 1. It's between 0 and 1. So we must make one estimate. And our estimate might be something like this. It's 0.9, right? That 0.9 is an estimate. I don't know for sure it's 0.9 based on this, but I'm estimating it about that. I did make an estimate and I stopped at that. I cannot say it's 0.9527 because I have no idea whether what this is true or not. I only know that this is close to true and I have to stop at that first estimate. Let's move the pencil down and use the next the higher precision ruler and see what we can say here. So here I look at the second one and I know, well, wait a minute, it's not 0.9, it's actually between 0.8 and 0.9. So I know for certain that we're dealing with a ruler that's going to be something that is 0.8. I know for certain that's the case, and I'm allowed to make, and I need to make one more estimate, almost all the way to the 0.9. So I might say that that is another 8. So I'd say this is a 0.88. That's my first estimate, and that's where I stop. So I get 2 decimals of precision out of this. And then finally, let's just be thorough. Move it down to the last one. And look at this one. Again, I know it's between 0.8 and 0.9, but now I also know, looks to me that it is between 0.89 and 0.90. So I have to make one estimation. It looks like it's just a hair over 0.89, so I might say that that is 0.891 would be my first estimated digit in that case. So that's how we're talking about. You have to make an estimated digit because that's telling people a little bit about your precision, but you cannot go more than one estimated digit because that's being dishonest, saying that you have more precise measurements than you really do. So again, let's take a look at this one. This is a triple beam balance, or quad beam balance rather, from our class. Chemistry in particular, we're using this a lot, but it gives us a little bit of practice. So again, we write down everything we know for sure. So in this case, I know we have 10 right here. I know that there's 8. So I add those together, that's 18. And then here's the one that takes a little interpretation. I would say that this is 18.8, I know. And I know we're not all the way up to the 0.85. We're somewhere in between 0.84 and 18.85. So I need to make, remember, one estimated digit. And to me, it looks like we're almost all the way over to that 0.5. So I would record this as best as possible. I think a number like this, and it would be in grams, would be our best decision here in this case. You may think it's an 8 here or a 7, or you may even go to 850, but the point is we have 3 decimals. That last one is an estimated digit. We have to make the estimation, but we have to stop at that one. So with practice, students usually find that making the measurements with correct number of significant figures is pretty simple. It's kind of obvious when you're using a certain tool. When you're estimating, you make that one estimation and you stop. But when you're reading other scientists' material and you see data from their experiments, how do you know about their precision and their accuracy? So in that case, we have to think about how are we going to count or determine what figures are significant. And there's a pretty easy way to do it. Any number that is not 0 was measured and it is significant. So the real question becomes then, when are zeros significant and when are they not significant? So here's an example. Here's Yao Ming at this strange measuring state. We're talking about 1 here. What is 1? I don't know. It's kind of arbitrary, but we might think about it as being 1 story tall. You know, Yao Ming's pretty tall, 7 foot something. So I would say he's definitely between 0 and 1. I get one estimated digit, so I'd say I think he's about 0.8 stories tall. So the question is this 2 digits or is this 1 digit that I measured in this case? And that's what we're going to take a look at. What do we do with that 0? Something on the opposite end might look like a tree here. I know the tree is between 0 and 700 feet tall. It'd be a very tall tree. So I could say maybe it's 600. I know it's between 600 and 700, so I'm going to estimate it that's about 650. I get to estimate that digit. Is this estimated or not, or is this just holding the place of the size? That's what we're going to take a look at next. So it turns out we have rules. They are on the PDF. That'll also be available on the Edmodo site. So I'll just look at them real quickly with you, but you definitely probably want to have these out with you. And we're going to go over a few of them. First of all, the first one I'm not going to spend much time on because if the number is not 0, it's significant. You do have to count it. But let's take a look at some of the other rules where there are zeros involved. Number 2 says zeros located between non-zero digits are significant. They count. So a measurement that might show this would be this arrow. I know for sure with this arrow that it's greater than 100, but it's less than 110. So I might estimate this at like 100 and maybe 103. That 3 is estimated. That 0 was part of the measurement itself. So that 0 is significant. So if the 0 is smashed between other non-zeros, it is significant and it does count. So what about trailing or leading zeros? Let's take a look at this measurement here. I know for this one that it's between 7,000 and 8,000. So I might guess, hey, this is about 7,500, 7,500. In this case, this was my estimation. I estimated that 5. These zeros serve to hold the place in that case. So in this case, there's actually only 2 significant figures, and that's what our rule number 3 is telling us. Trailing zeros, those at the end, are significant only if the number contains a decimal point. Otherwise, they're insignificant. So that's kind of strange. Just because it's insignificant doesn't mean that the number 0 is not important. This has 2 significant figures, the 7 and the 5. But 75 is a lot different than 7,500. So 2 significant figures is correct to say, but these zeros still matter. They're not significant. We're not going to count them as significant figures, but they preserve the size of the measurement. 75 is a lot different than 7,500. Both 75 and 7,500 had just two sig figs. The other arrow to the right would be sort of an opposite one. If we're looking at something like this, I know that we are between or really close to 100 there. I know that. But remember, I'm allowed to estimate one more digit, and I think maybe for me, I'm saying it's exactly at that point. So I might say that it's there. That's my last estimated digit. So in this case, all these zeros are significant because that's telling me something about the precision. They came from the measurement itself. So these ones do count because there's a decimal place in there. So there are 6 sig figs in that picture. Okay, and then the last one here. Let's take a look at just what the measurement would look at if we were making this measurement. I know that it is greater than 0.007. and it's less than 0.008. So I might estimate this at being halfway in between, 0.075. That 5 was the estimated digit. So these zeros are like the zeros on the big one. These are placeholders. We didn't necessarily, they preserve the size of the number, but they're not measured itself. So there's 2 significant figures in this case, and that's what we're saying with this rule. Zeros to the left of the first non-zero digit are insignificant. So here's our first non-zero digit. Zeros to the left are these ones. They're insignificant. And again, that doesn't mean they're not important. The number here is 75. 7 and 5 are significant, but that number is a lot different than 0.0075. So just because we say they're insignificant doesn't mean that we can ignore them in their meaning. So why does this matter? I mean, of course we want to be honest when we're sharing our data or reading other scientists' data. What do they know for sure? What do they know for certain, and what's an estimation? So sig figs matter in that regard, but they also matter because we're going to use them very often, these measurements, to do calculations. So imagine something as simple as this. We'll say speed today is as simple as distance divided by time. So imagine this little guy. He runs timer starts, the gun goes off, and he starts running, and he makes it here. And he does that in this amount of time. So I would take those two measurements and I'd say, all right, well, I know he's between 5 and 6 meters, so I could estimate him at 5.5 meters. And the time it took was 3.44 seconds. So I have a figure here with 2 significant figures and a figure here with 3. Now here's the important part. Watch what happens with our calculator. We put these numbers in. 5.5 divided by 3.44. Holy cow, look at that number. How can we get, how can we get a number with that many sig figs? I'm not even going to try to count them. When our measurements only had, the least had 2 amount of significant figures. And the answer is, well, your calculator and what you learn in math doesn't consider numbers to be measurements or have meaning. Scientists definitely do. So that number is gibberish in terms of the scientific meaning. We don't know someone's speed to that amount of precision. So where we're going next is, how do we calculate with these sig figs numbers? What are the rules? And they turn out to be pretty simple, but they are important. Just for future reference, if I see a number that long on anyone's paper in a chemistry or math class, I have to take points off. I'm physically compelled to do it because it doesn't mean anything.